Hello everybody, welcome into another lesson. So today we are going to talk about infinite and endpoint discontinuities for functions. So in the past two lessons we've talked about removable discontinuities, and then in the very last lesson we talked about jump discontinuities. Now today we'll talk about the final two types of discontinuities, with the first of the final two being infinite discontinuities. We have some arbitrary function graphed here, and as you see from either side, as you approach 0 from the left, this graph trails off towards negative infinity. If you approach 0 from the right, it trails off towards positive infinity. But in both cases, it never actually crosses where x equals 0. It's undefined there. So infinite discontinuities are caused by vertical asymptotes. And well, what functions have vertical asymptotes? You definitely have rational functions, that's a big one, logarithmic functions, and then four of your trig functions, the tangent, cotangent, secant, and cosecant functions, those also have vertical asymptotes. So those are the type of functions that are going to have infinite discontinuities. Now, if we look at this particular function, this one in particular is f of x equals 1 over x. So f of x equals 1 over x. As you see then, you have a vertical asymptote at x equals 0. That's where the infinite discontinuity is at x equals 0. So we can't define f of 0 in this case, because if you tried to, you would end up getting 1 divided by 0, making it undefined. But what we can do is we can say that the infinite discontinuity, so the discontinuity occurs at x equals 0. F of 0 does not exist, it's undefined, because 1 over 0 would give us an undefined value, but we can take left-handed and right-handed limits and then try to evaluate the general limit. So if we take the limit as x approaches 0 from the left of 1 over x, let's take a look at this here. I'm getting closer and closer to x equals 0, but I'm not actually touching it. And the closer and closer I get, the more negative my number's getting, the more larger and negative it's getting. So the limit as x approaches 0 from the left-hand side would be negative infinity. Now let's try to approach 0 from the right-hand side. So if we take the limit as x approaches 0 from the right of 1 over x, so let's go ahead and trace along this graph here. I'm getting infinitely closer and closer to x equals 0 from the right. I'm not actually ever going to meet x equals 0, but I'm getting infinitely closer to it. I'm going to continue to go up and up and up in my values until I reach infinity. So the right-handed limit would be positive infinity. Well, the left-handed limit and the right-handed limit do not match at all, so that means that the general limit as x approaches 0 of 1 over x does not exist, because your left-handed limit's negative infinity, your right-handed limit's positive infinity, and those don't match. So your general limit can't exist. And quite often, but not always, we're actually about to do an example here where the general limit can exist, even with an infinite discontinuity, but quite often you'll end up getting the general limit does not exist. And in fact, you'll even get somewhere one of the one-sided limits doesn't exist. We'll get into that too. But let me modify this a bit here. So let me just modify this just a bit here. This time, let's say I make f of x equal to 1 over x squared. So now I have an even power rational function, f of x equals 1 over x squared, the right branch hasn't changed, but what about the left branch? Well, since you're squaring your x values, the closer you get to x equals 0, the more positive it's going to get. So basically your graph is going to start to look something like this for f of x equals 1 over x squared. It'll look a lot like that. And I'm sure we're all familiar with the graph of f of x equals 1 over x squared. This is still an infinite discontinuity at x equals 0. That still happened. The reason being is, again, because we have no way to, we don't intersect x equals 0. We don't even touch it. We just get infinitely close to it. And f of 0 itself still not defined. We still can't define that. And that's true for all infinite discontinuities. At that particular point, you can't define the f value. So f of 0 does not exist because that would still give you 0 in the denominator. But we can take the left-handed limit and the right-handed limit. So if I take the limit as x approaches 0 from the left of 1 over x squared, then what I'm going to get, if I approach 0 infinitely closer and closer from the left, I'm going to approach infinity. So the left-handed limit would be positive infinity. Now what about the right-handed limit? So if I take the if I take the limit as x approaches 0 from the right of 1 over x squared, notice the closer I get to x equals 0 from the right, I'm going up and up and up until I reach positive infinity. So this time both my left and right-handed limits match. They both equal positive infinity. So we can actually say in this case that the general limit as x approaches 0 of 1 over x squared is positive infinity, since both the left-handed limit and the right-handed limits match. And this proves that just because you have an infinite discontinuity at a point doesn't mean you won't get a general limit at that point. You have to look at your graph and see what's going on, or know how your functions work as you approach from the left or right. Now let's do an example where you may even have one side of the function doesn't have a limit at all. So let's do f of x equals the natural log of x. Another common graph we deal with, the natural log of x. So let's see here, when x equals 1, y equals 0, and then it kind of goes up like this, and then it comes down like this for the natural log function. Well, what do we notice here? We have a vertical asymptote at x equals 0. So your discontinuity is going to be that x equals 0. In fact, we cannot define f of 0 because the logarithmic function in general, whether it's base e or any other base, it's not defined for any values less than or equal to 0. So f of 0 in this case does not exist. Now, what about the left-handed limit? What can we say then? The left-handed limit as x approaches 0 of the natural log of x, this is a good one because graphically we have nothing going on to the left of x equals 0. And that would have to mean that your x value is negative, which is not defined for the logarithmic function. So actually, the left-handed limit as x approaches 0 does not exist, which therefore already means the general limit can't exist. But what about the right-handed limit? If I take the limit as x approaches 0 from the right of the natural log of x, Notice the closer I get to x equals 0 from the right, I'm going down towards negative infinity. So the right-handed limit of the natural log of x as it approaches 0 is negative infinity. And just alone on the fact that the left-handed limit does not exist means that the general limit as x approaches 0 of the natural log of x does not exist. And of course, what would it be if we didn't do a trig function? We definitely need to do a trig function. Let's pick f of x equals cosecant of x. So f of x equals cosecant of x. Let's pick that trig function. Let me set up my trig values though. Here's going to be pi over 2. Here's pi. Here's 3 pi over 2. Then there's 2 pi. Alright, negative pi over 2. Here's negative pi. Negative 3 pi over 2. And then we have negative 2 pi. Alright, so as you know, for tangent, cotangent, secant, cosecant, you're going to have multiple vertical asymptotes. So we know x equals 0, of course, is a vertical asymptote. That's one of them, but why don't we pick something else? The next one, of course, is at x equals pi. In fact, any integer multiple of pi is going to produce a vertical asymptote. So we'll have another one here at 2 pi. So we have 0 pi, 2 pi. What else? Negative pi will have a vertical asymptote. And then we'll have yet another one at negative 2 pi. Alright, so from 0 to pi represents the first quadrant. We know the cosecant of pi over 2 is 1. Then our graph is going to go up like this. And then, well, from 0 to pi, I should say, is the first and second quadrant, excuse me. From pi to 2 pi, that represents a third and fourth quadrants. So at 3 pi over 2, the cosecant is negative 1. And our graph goes down like this. So it just continues to repeat. We know what the graph of cosecant looks like. I know we graphed the heck out of it in pre-calc, and in Algebra 2 trig we did that. I'm just drawing it here. By now I would assume everyone's familiar with the graph of basic trig functions. I'm just doing a good graph of it. So take your pick of any vertical asymptote, and those are your infinite discontinuities. And this does it infinitely, but what if we just focus on x equals pi? We definitely have a discontinuity at x equals pi. Which means, in that case, if the discontinuity is at x equals pi, the infinite discontinuity exists there, that means that f of pi itself is undefined. It does not exist. And that makes sense because cosecant's the reciprocal function of sine. The sine of pi is 0, while 1 over 0 is undefined, so f of pi does not exist. Now, let's explore the limits. So what about the limit as x approaches pi from the left of cosecant of x? So I'm going to go trace along the curve. I get infinitely closer and closer to pi from the left-hand side. I just keep going up and up and up. So the limit as x approaches pi from the left of cosecant of x is infinity. Now we can deal with the right-handed limit as x approaches pi. So the limit as x approaches pi from the right of the cosecant of x. Let's trace along the graph, get infinitely closer and closer to x equals pi from the right. As you see, I'm going downward. I keep going down towards negative infinity. So my right-handed limit as x approaches pi of the cosecant of x is negative infinity. And since the two limits don't match, that means the general limit as x approaches pi of the cosecant of x does not exist. So really, as we proved in the second example, there will be times your general limit will still exist even though you have an infinite discontinuity at that point. You just have to understand what the graph is doing and understand what the function is doing at that particular value of x in order to be able to answer, does it have a general limit or not? But one thing is always true, f of that value, the value of the function at that value of x will always not exist because an infinite discontinuity again is just simply a vertical asymptote. So that's it for infinite discontinuities. The last type are called endpoint discontinuities, and we'll get into those. Alright, so of course there are endpoint discontinuities. These are a little less common than the other three, but they're simple enough to understand. Endpoint discontinuities, let's say I have some graph here that just has a point here and over here, but in between I have the graph of some curve, arbitrarily. Endpoint discontinuities occur from man-made conditions, like restricting the domain. This could be the graph of a normal function that would continue on forever, but for whatever reason, the domain's been restricted by a person. Well, that's where an endpoint discontinuity comes in. So in this case, your domain, if we go to the left, 1, 2, 3, 4, it starts at x equals negative 4 inclusive to 1, 2, 3, 4, 5. My domain is from an x value of negative 4 to positive 5, or in this case, I could simply end up saying negative 4 is less than or equal to x, which is less than or equal to 5. That's another way you may see the domain written for this function. Now, at the endpoints here, the good news is f of those values are defined. So, if I want to take f of negative 4, I could certainly find that. F of negative 4 gives me positive 4. Because I have the solid dot. Those are defined. Now, what about at f of positive 5? At f of positive 5, I get a y value of 2, so f of 5 is going to equal 2. So with endpoint discontinuities, at those particular endpoints, and of course any point in between, you can take the value of that function and actually get an answer. But where it gets interesting are your limits. So let's take the limit as x approaches negative 4 from the left. If we take the limit as x approaches negative 4 from the left, well, negative 4 from the left, what does that mean? Let me write the f of x. Negative 4 from the left means that x is less than negative 4. Well, if we look at our domain, and we even look at the graph, we don't have any values for x is less than negative 4. So the left-handed limit does not exist. Now the right-handed limit will exist. The right-handed limit as x approaches -4 of this function. If we go along the curve, trace along the right till we reach x equals -4, that's going to be that y value of +4. But the general limit fails to exist because the left-handed limit doesn't exist. So the general limit as x approaches -4 of this function does not exist because the left-handed limit doesn't exist. In fact, with endpoint discontinuities at the endpoints, so you can define the function value and you'll find a one-sided limit there, but the general limit will always fail to exist at endpoint discontinuities. Now, of course, we can deal with x equals 5. Why don't we take that? Let's deal with the limit as x equals 5 of this function. So the limit as x approaches 5 from the left of this function, if we take this curve, we trace along the graph from the left, we approach 5 from the left, we're approaching that y value of 2. So the left-handed limit is going to be 2, but what about the right-handed limit? The limit as x approaches 5 from the right of this function. Well, let's look to the right of 5. That would have to mean that x is greater than 5, which it's not defined. So the right-handed limit in this case doesn't even exist, which means since the right-handed limit doesn't exist, the general limit at x equals 5 of this function also does not exist. So with endpoint discontinuities, once again, you'll be able to find the function value at your endpoints. You'll get a one-sided limit at those endpoints, but the general limit will fail to exist. Let's do an example of a function that actually has an endpoint discontinuity. I'm going to deliberately restrict the domain to illustrate this. Let's say I take f of x equals the cosine of x. Yes, I'll actually do a trig function where 0 is less than or equal to x, which is less than or equal to pi. I'm going to restrict the domain from 0 to pi. So let's see, here's pi over 2, and then here's pi. Alright, so what is the cosine at 0? When we graph it, it's going to be a y value of 1. Then we know at pi, that gives you -1. Of course, pi over 2 is 0. But let's go ahead and graph this function, and we get this little piece here. We know that normally the cosine of x is defined for all real numbers. Sine and cosine are defined for the entire set of real numbers. It would keep going on infinitely. But that's not true in this case because the domain is just restricted from 0 to pi. So what does that mean? Well, we see that still, even from the domain and graphically, since you have the solid dots, that you can get the function value at f of 0. So f of 0, of course, means the cosine at 0, which we know to be 1. And then the other endpoint is pi. We can take f of pi. We know the cosine at pi is -1. So we got our function values at the endpoints. But let's take the limit as x approaches 0 from the left of the cosine of x in this particular case. Now keep in mind, normally you would have a general limit at x as x approaches 0 of cosine of x. Normally whether you approach from the right or left, that limit would be 1. But since we're we have a restricted domain from 0 to pi, left of 0 means that x is less than 0. Well, it's undefined in this case since the domain's restricted. In this case, the left-handed limit fails to exist. But we can certainly take the right-handed limit of this function as x approaches 0 from the right of the cosine of x. Well, that would get us close to a y value of 1 or put us at 1. So the right-handed limit exists, but in this case the general limit is going to fail to exist at x equals 0 because the left-handed limit does not exist. Because with endpoint discontinuities, we don't care what's going on to the left of the left endpoint. We don't care what's going on to the right of the right endpoint. We only care what's actually going on at the endpoints themselves and in between those endpoints. That's all we care about. Then, of course, let's look at the other endpoint, pi. The limit as x approaches pi from the left of cosine of x, trace along the graph here, you get to a y value of -1. So the limit as x approaches pi from the left in this case is -1. However, let's take the right-handed limit. The limit as x approaches pi from the right of this particular function would normally also be -1, but the domain is restricted where it only goes from 0 to pi. Pi from the right means we have values of x greater than pi, which in this case is undefined, which means the right-handed limit in this case fails to exist. So that means that the general limit as x approaches pi for this function cannot exist, because the right-handed limit doesn't exist. So again, to recap for endpoint discontinuities, these are always man-made. They're always man-made because the domain is restricted. Except for, I would say, in the case of the square root function. You know what? Let's look at that. Radical functions are usually the only exception. That has an endpoint discontinuity on its own. So, for example, f of x equals the square root of x. Well, it definitely is. It's even defined at x equals 0. There's no vertical asymptote, so it's not an infinite discontinuity, but we know the square root of x is not defined for any values less than 0. So at 0 itself, you would get a y value of 0, and then we know the square root function is going to go something like this. It just keeps going infinitely and infinitely. But you have a left endpoint at x equals 0 all on its own. That's the only time an endpoint discontinuity occurs naturally. Any other time except for the square root function, it's going to be man-made. But the common theme is that you can find the value of x at that particular endpoint or endpoints, but the general limit will fail to exist. Of course, let's say I want to find, well, the domain in this case, of course, is where x is greater than or equal to 0. Or you could also say from 0 inclusive to infinity non-inclusive. That's your domain. And we can even take the value of f of 0 would give you 0. But let's look at the left-handed limit as x approaches 0. The limit as x approaches 0 from the left of the square root of x, well, that has to mean that x is less than 0, which is not defined in our domain and definitely not graphically. So the left-handed limit's going to fail to exist, but the right-handed limit's going to exist. We take the limit as x approaches 0 from the right of the square root of x. That's just going to give you 0. But since the left-handed limit doesn't exist, the general limit as x approaches 0, in this case, does not exist because of the fact that you can't take a left-handed limit of it. So that's actually a trick there, because the general limit as x approaches 0 won't exist because you can't take the left-handed limit of it. So that's it for this lesson. In the very next lesson, we're going to combine all of these discontinuities together into one. This is going to be a lesson called Crazy Graphs, where you have to figure out at what points the discontinuities occur, what type of discontinuity they are, evaluate their limits, and if possible, find the value of the function at that particular point. So I hope everybody has a great day. Take care.